Okay, good afternoon, guys. So we're going to pick up where we left off last time, and that was with the proof technique of induction. So to refresh your memory, when we do a proof by induction, we're really doing a few parts. Okay, the first part is called the basis step. And that's when we prove that the claim is true for the smallest value to which the claim applies. So if the claim applies to all positive integers, then the smallest positive integer is the value we prove that it's true for. The smallest positive integer is 1. Won't always be that way, and we'll see examples in a second. The second thing you do is you state your inductive hypothesis. So you assume that the statement is true for some arbitrary value of k. We usually use k. And that's the assumption you'll get to make, because you remember you're trying to prove that for all k, pk implies pk plus 1, where p is the statement you're trying to prove. All right, so if we're going to do that, then if we want to apply universal generalization at some point to get to that universally quantified statement, what we have to do is let k be arbitrary. And we already saw that at the beginning of the course. So at that point it becomes, well, we need to prove pk implies pk plus 1 without a for all, but only if k is arbitrary. So that's an implication, and if we have to try to prove an implication, typically what we'll do is we'll do a direct proof, and we'll assume that the thing on the left is true and try to prove that the thing on the right is true. The thing on the left is called your inductive hypothesis. And then step 3 is to do the inductive step. And that is to prove that pk plus 1 is true under the assumption that pk is true. All right, that was what we decided was a proof by induction. So what I'd like to do today is several more examples of how to do that. I ended last class saying that there's nothing special about starting at 1. Right? It won't always be that you prove P1. You want to prove that the statement is true for the smallest value to which it applies. So I'm going to do an example now where that is 0. So this example, we'd like to prove that 2 to the 0 plus 2 to the 1 plus 2 to the 2 plus all the way up to 2 to the n is equal to 2 to the n plus 1 minus 1. For all non-negative integers n. So in the previous examples, n was usually taken to be any positive integer. Now we're going to take it to be any non-negative integer. The set of non-negative integers and the set of positive integers are almost the same, except for 0. Right? 0 is non-negative, but it's not positive. So 0 is neither positive nor negative. So 0 is included in this claim. And 0 is the smallest thing included in this claim, so that's why our basis step will be for n equals 0. So we start with our basis step. And I like to write down what the value of n is, just so it's completely clear. So in this case, the left-hand side is just 2 to the 0. I'll say LHS equals 2 to the 0 for left-hand side. And 2 to the 0 is, of course, 1. The right-hand side, well, if n is 0, then n plus 1 is 1 minus 1. So 2 to the 1 is 2 minus 1 is 1. And we see here that the left-hand side is indeed equal to the right-hand side, so the basis step is true. Right? The basis step is correct. So we verified that, which means now we move on to proving the inductive step. But before we do that, I usually like to write down my inductive hypothesis. So the inductive hypothesis here is what? What's going to be my inductive hypothesis here? Any thoughts? Yep.
Does it have a summation notation in it?
You could. Yeah, you definitely could write it. You don't have to write it that way. You could write it with these ellipses as I've written in the statement. Either is completely fine. Yep.
would be like what you've written up there, 2 to the 0 plus 2 to the 1, all the way to 2 to the k equals 2k plus 1 minus 1.
Yeah, exactly. Right? We assume that it's true for n equals k. So we assume that for some arbitrary k. Notice I don't say for all k, because if I said for all k, I would be assuming what I have to prove, and that's not valid. So now that we have our inductive hypothesis, the next step is to do the inductive step. And you should always, always, always write down what it is you're trying to prove. Because that way, even if you're not successful in your proof, the TAs at least know that you know what induction is. And that's what we're trying to teach you in this course. All right, so what is it that I'm trying to prove in my inductive step? What's my goal? Yeah?
You're trying to prove that the left side equals the right side?
Yeah, so what is the left side in the inductive step?
The sum.
Okay, so the sum is 2 to the 0 plus 2 to the 1 plus 2 to the 2, all the way up to what? Well, 2 to the k is the sum I'm interested in my inductive hypothesis. What am I interested in here? Yeah? Right, I want to go all the way up to 2 to the k plus 1. I'm assuming that the sum of the first k powers of 2 is something. Well, the first k plus 1 powers of 2. And now I want to prove that the sum of the first k plus 2 powers of 2, including 0, is something. So that's the left-hand side. So we want, what's on the right-hand side? 2 to the k plus 2 minus 1. Right? So that's k plus 1 plus 1, which is just k plus 2. So this is what I have to prove. That's what I'm going to be aiming towards. Is it clear why I want to prove that? So you basically, to figure out what you have to show in your inductive step, you sub in k plus 1 for n in the original statement. Just like in your inductive hypothesis, you sub in k for n. Does that make sense? Yeah?
Does that hold for all inductive proofs? Did you sub in k plus 1?
So we'll see some examples where the n isn't quite as clear. You'll do an operation that's very similar, so the spirit of what you'll do is always that, but sometimes the implementation of it is a little bit different. But that's always the idea, yes. Other questions? Yeah?
Are all inductive proofs for like infinite things? Like things that go to infinity?
Yes. So in fact, if this broke down somewhere, you would not be able to complete this proof. Something bad would happen somewhere. Other questions? All right, so we want to prove that the thing on the left is equal to the thing on the right. So we start with the thing on the left, which is 2 to the 0, plus 2 to the 1, plus 2 to the 2, all the way up to 2 to the k plus 1. And I want to apply a bunch of rules to try to get myself to the other side. That's my goal. And in doing that, I want to look for opportunities to apply my inductive hypothesis. That's the trick to inductive proofs. The reason we make that inductive hypothesis, the reason we have it, is so that we get leverage. If you don't use it anywhere, there's no point in doing a proof by induction. You'd be better off doing some other proof technique, which you'll either be able to do and be happy, or you won't be able to do because you really needed that leverage after all. So we need, or want, to take advantage of the fact that 2 to the 0 plus all the way up to 2 to the k is equal to this thing here, 2 to the k plus 1 minus 1. So we'd like to use that somewhere. Is that sum anywhere here, though? It almost is, but the reason it's not exactly here is because I've written this in a very funny way. It's exactly the same to write this is 2 to the 1 plus 2 to the 0 plus 2 to the 1 plus 2 to the 2, all the way up to 2 to the k, and then plus 2 to the k plus 1. Right? That's the exact same sum. I'm just writing more of the terms. So I'm taking the 2 to the k out of the ellipsis. And at this point, you say, oh, I already know something about this. right? That's exactly what my inductive hypothesis covers. This thing is equal to 2 to the k plus 1 minus 1. And then I still have this other 2 to the k plus 1 out here. And this is by the inductive hypothesis. Does everyone see how I applied that there? Yeah?
Can you go over how you got to the k plus 2?
Here? Yeah, so I sub in k plus 1 for n in the original statement. So the original statement is 2 to the 0 plus 2 to the 1 all the way up to 2 to the n equals 2 to the n plus 1. So if I sub in k plus 1 for n, I get the sum up to 2 to the k plus 1 equals 2 to the k plus 1 plus 1. So 2 to the k plus 2. And then minus 1 outside of the exponent. All right, so now that I'm here, I can just rearrange this a little bit. I have 2 times 2 to the k plus 1 minus 1, and that's exactly the same as 2 to the k plus 2 minus 1. Okay, and if we look back at what it is we wanted to show, it's exactly the right thing. 2 to the k plus 2 minus 1, 2 to the k plus 2 minus 1. Does that make sense? So when you do a proof by induction that some summation equals something, this is the common trick, right? We have some bigger summation, so we leave off the terms we don't know about, apply the inductive hypothesis to the terms we do know something about, and then do some manipulations and hope that everything works out. Okay, this is a common technique. We'll see this a couple of times. Other questions about this? Okay, so let's do another summation example, and this time I'm not going to use the ellipsis. I'm going to actually write out the sum. So here's the example we do. We already saw this, but I didn't really prove that it was correct. I derived it for you, so you got the idea. But I'm going to prove it in a different way now. I'm going to prove that the sum from I equals 0 to n of a times r to the I, which is the same as a plus ar plus ar squared plus ar cubed all the way up to ar to the n. I'm going to prove that that is equal to a times r to the n plus 1 minus a over r minus 1. Okay, and this is as long as r is not 1 and n is at least 0. Okay. Sometimes I won't specify the value of n here, and in that case it's up to you to figure out what the base case should be, the basis step should be. When you're given a sum, it's usually easy to figure out what it is just by examining the sum. So this sum goes from I equals 0 to n, so the smallest value of n that makes sense is 0. So if I didn't say any restrictions on n, you should assume that n is at least 0. Okay, but typically I'll tell you what it is. So is it clear what's being asked here? I want to prove that this sum has closed form ar to the n plus 1 minus a all over r minus 1. Okay, we've already seen this when we were talking about the sum of a geometric sequence. All right, well, if we're going to do that, we'll do the usual proof by induction. So we start with a basis step. Here the basis step is n equals 0 because it says n greater than or equal to 0. So n equals 0 is our basis step. And we do the usual trick. We have the left-hand side. Well, that's the sum from I equals 0 to 0 of ar to the I. Yeah, so that's just a. This is the same as ar to the 0, and that's a times 1, which is a. The right-hand side, well, that's ar to the 0 plus 1 minus a over r minus 1. Right? All right, well, in this case, what do we have? Yeah, so we need to do a little bit more work than we're used to. This thing here is the same as AR minus A over R minus 1. So what we can do is factor out the A from the top, like you suggested. And that leaves us R minus 1 over R minus 1. These R minus 1's cancel, which gives us an A. So this is a little bit more work than the other basis steps we've done, but it's still not too bad, right? All we had to do was factor AR minus A, which we should be able to do at this point. Notice that the only reason this is valid is because R does not equal 1. If R were equal to 1, I'd be dividing by 0, and I couldn't do that. So this is the basis step. Does that make sense? All right. So next we do the inductive hypothesis. And the inductive hypothesis is that we assume that the statement is true when n equals k. So the statement when n equals k is that the sum from I equals 0 to k of AR to the I is exactly the same as AR to the k plus 1 minus A over R minus 1. That's it. And we assume this is true for some arbitrary k. Again, that's not all k, it's just some arbitrary k. All right, so now that we have our inductive hypothesis, we now go to our inductive step. And the first thing we do in an inductive step is to write down what it is we want to show. Want to show that the sum from I equals 0 to k plus 1, right, because we sub in k plus 1 for n now, of AR to the I is equal to AR to the k plus 2, right, k plus 1 minus A over R minus 1. That's what it is we'd like to show. Does everyone see that that is the inductive, or what we have to prove in the inductive step? All right. You will need to do these for every single inductive proof. So if you don't understand what's going on, it's important that you get help at this point. All right. So we want to prove this equality. So we start on one side and work our way to the other side. And the simplifications we do should somehow let us use our inductive hypothesis. That's the point of these. I'm never going to ask you one of these where you don't need your inductive hypothesis. All right, so the sum from I equals 0 to k plus 1 of AR to the I. Well, I know something about the sum from I equals 0 to k, but I have the sum from 0 to k plus 1. So one thing I can do is I can split this sum up into two things. This sum is exactly the same as the sum from I equals 0 to k of AR to the I, but then I have to add on that last term myself. What is the last term in that sum? AR to the k plus 1. This is almost always what you want to do for these summation kind of questions. All right. So now we know what that thing is. We know this sum by our inductive hypothesis is just AR to the k plus 1 minus A over R minus 1. And we have this AR to the k plus 1 out here. So it looks like we're in pretty good shape. We just need to do a little bit more work to get it into the same form so we're sure that it's correct. If I want to add on this AR to the k plus 1, I need a common denominator. And the common denominator should be R minus 1. So I have AR to the k plus 1 minus A over R minus 1 plus R minus 1 times AR to the k plus 1 over R minus 1. Right? I found a common denominator of R minus 1. That's okay? You're comfortable doing addition of fractions? All right. So now I can write this out all as one long numerator. AR to the k plus 1 minus A plus R minus 1 times AR to the k plus 1. And this is all over R minus 1. And things are looking good because I don't have any summations, but I'm not quite where I want to be. I'm shooting for AR to the k plus 2 minus A over R minus 1. I already have the denominator that I want, r minus 1. So I just need to work with the numerator a little bit to get it where I want it. So the first thing you should do is distribute this ar to the k plus 1 over the r minus 1. So ar to the k plus 1 minus a plus r times ar to the k plus 1 minus ar to the k plus 1. And this is all over r minus 1. So who sees what to do now? Yeah, I have plus ar k plus 1 over here and minus ar to the k plus 1 here. So I can cancel those. And I can rearrange the other two terms to give me r times a to the r times a times r to the k plus 1 minus a over r minus 1. And now I'm very close to the answer. What's the last thing I have to do? Yeah?
The r is equivalent to r to the power of 1 by multiplying it by the r to the power of k plus 1 becomes r to the power of k plus 2.
Exactly. I take the r that's out in front and I increase the exponent by the other r by 1. So this is exactly the same as a times r to the k plus 2 minus a over r minus 1. And that looks pretty nice. So I go back up to what I'm trying to prove. And I was in fact trying to prove that the sum was equal to a times r to the k plus 2 minus a all over r minus 1. So that's exactly what I wanted it to be equal to, and it is. Okay, so now the proof is done. The inductive step is proven. Questions about this one? Yeah? This k plus 2? Yeah, so we have r times r to the k plus 1. So the exponent of the second r increases by 1 and the first one disappears. Yeah?
On the right-hand side, where did that summation?
What summation?
At the induction step, at the start of the induction.
This right here?
No.
This over here?
No, down.
This one here? Yeah, so the sum from I equals 0 to k plus 1 is the same as the sum from 0 to k plus that last term. Right? It's just a different way of writing the summation. If I want to sum up from 0 to k plus 1, one way to do that is to sum up from 0 to k and then sort of add on the last term manually, if you like. Other questions? So this kind of trick is almost always what you'll do for these. All right, so the next one is a similar inductive proof, but it does have a trick in it. I'm warning you that it has a trick in it right now. So there's these things called the harmonic numbers, and the jth harmonic number it's denoted h sub j, and it's defined as h sub j equals 1 plus a half plus a third plus a fourth plus all the way up to 1 over j. That's the jth harmonic number where j is at least 1. Okay, those are what the harmonic numbers are. You add up all the reciprocals. All right. The claim is that h of 2 to the n is greater than or equal to 1 plus n over 2 for all non-negative integers n. So the 2 to the nth harmonic number is at least 1 plus n over 2. So this tells you that the nth harmonic number is about y. Is the claim clear? All right. So we do the usual thing. We start with a basis step. In the basis step, we prove it's true for the smallest number that the statement applies to. This applies for non-negative integers n. So that means I start at 0. So if I start at 0, the left-hand side is h of 2 to the 0, which is just h of 1, which is 1 over 1, which is 1. That's okay? The right-hand side is 1 plus 0 over 2, which is 1. And it happens that these are equal, but remember we weren't looking to check if they were equal. We just wanted that the left-hand side was greater than or equal to the right-hand side. So we're happy. It happens that they're equal, but if they're equal, they're also greater than or equal. Is that okay? All right, so now that we have that, we do our inductive step. In the inductive step, we assume yes, sorry, I meant the inductive hypothesis. We assume that h of 2 to the k is greater than or equal to 1 plus k over 2 for some arbitrary k. Now, to be fully correct, you would say some arbitrary non-negative integer k, but it's clear from context that that's what k is. Okay, so that's our inductive hypothesis. And the next thing we do is the inductive step. So in the inductive step, we want to show that h of 2k plus 1, and that plus 1 is all in the exponent, is greater than or equal to 1 plus k plus 1 over 2. Right? We just sub in k plus 1 for n. All right, so we want to prove an inequality, and the way you prove an inequality is you start on one side and you work your way to the other. You definitely don't write down this inequality and do stuff to both sides. That's not how you prove an inequality is true, unless everything you do is if and only if. All right, so the first side, the left side I will start on is h of 2k plus 1. So let's write down what exactly that is. It's 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4, all the way up to 1 over 2 to the k plus 1. That's what that is. And the usual trick that we do is we try to take out the little bit of the sum that we're interested in. Right? So we're interested in 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus all the way up to 1 over 2 to the k, because we know something about h2 to the k. But what's left after I do that sum? So in the harmonic numbers, the number after 1 over 2 to the k, what is that number? Yeah? Okay, but there's two ways to parse what you just said. What's the correct way? So where are the brackets? Yeah? Right, the 1 is not part of the exponent, right? Because it's always 1 more than the last one. So 1 over 2 to the k plus 1. So this plus 1 is not in the exponent. The thing after that is 1 over 2 to the k plus 2. And this continues until I get to 1 over 2 to the k plus 1. So that's really important, because in the previous two examples, once I left off something, I only left off one thing. In the previous examples, I had the inductive hypothesis plus one extra term. Here I don't have the inductive hypothesis plus one extra term. I have the inductive hypothesis plus a bunch of extra terms. So this is equal to h 2 to the k plus, and I'll write this out bigger so you can see it now, 1 over 2 to the k plus 1 over 2 to the k plus 2 plus 1 over 2 to the k plus 3 plus all the way up to 1 over 2 to the k plus 1. So how many terms are there on the right? Question first?
Yeah. Can you explain the steps again, why it's 2k plus 1?
Right, so in the harmonic numbers, it's always 1 over a number. The next harmonic number is 1 over the next number, then 1 over the next number. The number right after 2 to the k is 2 to the k plus 1. It's not 2 to the k plus 1. Right? The number after 2 to the 3, which is 8, is 9. It's not 2 to the 4, which is 16.
Right, so the number of terms after, or no, yeah.
Yep.
I was wondering, is it okay to sub in h to the k, even though it's greater than or equal to in the inductive hypothesis?
Right, so I'm not applying the inductive hypothesis. I'm just applying the definition of the harmonic number here. Yep.
Are the number of terms between 2k and 2k plus 1 finite or infinite?
They're finite. There's finitely many. It depends on the k, but there's finitely many when k is finite. Yep. It's not quite k. Not quite 2 times k. There's a lot of them. So, what is another way of writing 2 to the k plus 1? 2 times 2 to the k. So I start off at 2 to the k, and I want to go to 2 times 2 to the k. So how many terms do I have? 2 to the k. So there's 2 to the k terms here. Does that make sense? All right. So now we're ready to start applying some stuff. I want to write down 2 things that are definitely smaller or equal. The first thing is from my inductive hypothesis. I know that h 2 to the k is at least 1 plus k over 2. I know that by my inductive hypothesis. That's okay? And now I want a lower bound for the thing on the right. So I want to know what's the smallest the thing on the right could be. Well, I need to get it pretty close, and the way I'll show you what it is the following. What's the smallest term in these 2 to the k terms? Right. The smallest term will be the one with the biggest denominator. So the smallest term is this one here. And how many terms are there? There's 2 to the k. So one way I can get a lower bound on that sum is I multiply the smallest term by the number of terms. And that'll give me a lower bound on how big the sum is. So if I have a bunch of numbers, let's say I have 10 numbers, and they're all at least 5, then I know their sum has to be at least 50. Does that make sense? Okay. So that means this thing here is at least 2 to the k many terms times 1 over 2 to the k plus 1, because that's the smallest term. So let me write that out. This is the smallest term, and this is the number of terms. You could do the exact same trick to get an upper bound. You would say it's less than or equal to the number of terms times the largest term. That would do the same kind of thing, but in the other direction. All right, so now we're kind of happy because we've got rid of all of the ellipses. And now we have something simple that we can work with. So let's do that. We have 1 plus k over 2 plus 2 to the k over 2 to the k plus 1. So what is 2 to the k over 2 to the k plus 1? It's not quite 1 over k. It's going to be 1 over 2, right? And the reason is, well, who knows the reason? Yeah?
You subtract the exponents, then you get 2 to the negative 1.
Right. When you divide 2 powers of 2, you subtract the exponents. So this is k minus k plus 1, all in brackets. So this thing here is 2 to the k minus k plus 1, which is the same as 2 to the k minus 1, and 2 to the minus 1 is a half. Yep?
Can you explain how you got the term on the third line there, 1 plus k over 2?
This here?
Yeah.
Yeah, this is from my inductive hypothesis. I know that h2 to the k is at least 1 plus k over 2. And I have h2 to the k there. All right, so that means this is 1 plus k over 2. Whoops. 1 plus k over 2 plus a half. And now if I add that, I get k halves plus 1 halves is k plus 1 many halves. And 1 plus k over 2, 1 plus k plus 1 over 2 is exactly what I had to prove. So that shows that the 2 to the kth harmonic number is at least 1 plus k over 2. And in fact, it's pretty close to that, but I won't show the upper one. Any questions about this proof? So this is a tricky one, right? This is a tricky one because when we went to the next term, we had a whole bunch more terms really. Because we didn't go to the next term, we went to the next value of k, and that added 2 to the k many terms. The way you know that's going to happen is because the index that you're interested in isn't just k, it's 2 to the k. Right? So when you increase k, you're not going to increase the number of terms by 1, you're going to increase it by 2 to the k. Does that make sense? All right. So, the next example we'll do is revisit something again that we did earlier in the course. So earlier in the course we were talking about power sets, and we said that the size of the power set of a set of size n is 2 to the power n. And what I'd like to do now is prove that for you. So prove that the size of the power set of a set of size n, whoops, is 2 to the n. That's what I'd like to do. All right, so we start with our basis step. And in this particular statement, it's not clear, or at least it's not explicit, what n is. What is the smallest n that makes sense for this statement? 0, because n is the size of a set. And the smallest that a set can be is 0. There are sets of size 0. There's one of them. It's the empty set. So the basis step is n equals 0. So if that's the case, then the set is empty. Since n equals 0, the set is the empty set. There's no other set that has size 0. It's just the empty set. And in this case, what is the power set? Well, the power set isn't empty. Yeah? Yeah, the power set is the set that contains the empty set. Because the only subset of the empty set is the empty set itself. All right, so if that's the case, then the size of the power set is the size of this set. And what's the size of that set? 1. Question?
Yeah, the power sets are the set of every single subset.
Yes. All right, so in this case, n is 0, and the size of the power set of a set of size n is 1, which is 2 to the 0. So this shows that the claim holds in the basis step. Does everyone agree with that? All right, so in the next step, we'll do our inductive hypothesis. And here we assume that the size of the power set of a set of size k is 2 to the k. So assume that the size of the power set of a set of size k is 2 to the k. All right, we just sub in k for n in the original statement. And the inductive step will be, well, we want to show that the size of the power set of a set of size k plus 1 is 2 to the k plus 1. And the k plus 1 is all in the exponent this time. So we want to show that the size of the power set of a set of size k plus 1 is 2 to the k plus 1. And one thing you might notice about what's happening here is we're not just proving some equation is true. I mean, we kind of are, but the equation's in disguise a little bit. Right? This statement that we're trying to prove is mostly in English. And that's something we'll talk about a little bit more later on. But induction applies perfectly well here. This particular example outlines a very common mistake and really highlights that you cannot make it. So what do we want to prove? We want to prove that the size of the power set of a set of size k plus 1 is 2 to the k plus 1. So that means you are given a set of size k plus 1. You are not given a set of size k. Okay, this is just like in the other examples. In all of the other examples in the inductive step, I wanted to show it's true for k plus 1. So on the left-hand side, or whatever I start with, I have the case where it's k plus 1. So that's true here. That's true here. I have a k plus 1 there. That's true here. I have a k plus 1 here. I never start with the k. I always start with the k plus 1 and try to get the k. That's really important. So it's the exact same here. I'm going to start with the k plus 1. Did I change the size? There we go. I'm going to start with the k plus 1 and try to do something to get to k. You do not start with the k. That's one of the most common mistakes in a proof by induction. Can you add two sets together? Yeah, so you can do things to the sets, but the important thing is that you're starting with a set of size k, k plus 1. So, let S be a set of size k plus 1. If you start this proof by saying let S be a set of size k, the TAs will be very annoyed. So don't do that. Let S be a set of size k plus 1. And now we want to get down to a set of size k. And the reason we want to do that is because we know something about a set of size k, right? We know that its power set has size 2 to the k. But right now I have a set of size k plus 1, so I need to do something to it. And the thing I'll do to it is take an element out of it. So what I'll do is I'll write S equals S prime union A, where A is just some element. So where A is in S, and S prime is just S minus A. So S prime is the same as S, except one element has been removed. And that element is A. A is some variable. So this is a very common trick with induction, right? I said the rule is you have to start with k plus 1, but typically you want to work towards k. That's almost always what you want to do. So I started with k plus 1, and the way I'll get to k is by removing something. But that's only valid if there's something to remove. Right? What I just did doesn't make any sense if S is empty. Right? That would be invalid because I'd be removing something from an empty set. Why am I allowed to remove something from S? Yeah?
Because you added 1 to it, so you don't get something there. Or, because it's the size k plus 1, so if k is 0, then it is the full size.
Right. So I'm removing something from a set of size k plus 1, and k is at least 0. So that means k plus 1 is at least 1. So that means there's definitely something in that set for me to remove. Okay? This is a very easy mistake to make. And there are proofs that don't really work but seem like they do, and the reason why is because of this. We'll maybe see one on the tutorial next week. So it's really important to understand that. I'm only allowed to remove something from S because I know that there's something there to remove. All right. So now that I have S prime, I think about what are the subsets I can generate in S. So let's look at the subsets of S prime. We know something about those. So for each subset, let's call it X of S prime, there are 2 subsets of S, right? There's X and X union A. So look at all of the subsets you get of S prime. And remember, S prime does not have A in it. So if you look at all of those subsets, well, you can get a subset back in S by taking that exact same subset, because it's still a subset of S, but you get another subset by taking that subset and adding A back in. And you know that that always produces a different subset because A is not in S prime, right? S prime is S minus A, so A definitely can't be in S prime. A itself, so in that case, that would come when you look at the empty set as a subset of S prime, and then the empty set union A would be A on its own. All right, so that's the first remark. For every subset of S prime, there are 2 subsets of S. For every subset of S prime, there are 2 subsets of S. And I know that because each X is distinct, and therefore each X union A is distinct. All right. So now we're getting close. The number of subsets of S, oops, well, it's kind of like the number of subsets of S prime, but it's times 2. Because every subset of S prime generates 2 subsets of S. And the only question that remains is, are there any subsets of S that aren't generated in this way? So have we missed any? So we haven't missed the empty set because remember, X here could be the empty set, and X is also a subset of S. Yeah?
The set itself?
So the set itself will be when X is S prime itself, and then you have S prime union A, which is exactly S. Yeah? So the set just consisting of A is when X is the empty set, and I look at this subset there. So in fact, I'm not missing anything. And the reason I'm not missing anything is every single subset of S either contains A or it doesn't. Right? Those are the only two possibilities. A can't kind of be part of the subset. And all of the ones where it is contained live over here. All of the ones where it is not contained live over there. So that means every single subset is generated. Does that make sense?
Yeah, but can you write that as the first?
Yeah, so that's exactly what you'd say. You'd say that up here. Every subset of S is generated in this way. And I don't have room, but you would say because because for every subset of S, either A is present or it's not. Yeah?
You're saying, say for each subset, there are two subsets, you're saying there exist two, right? Not there's only two?
There are exactly two. Right? But that's for every single S. So if you gave me a subset of S prime, I would give you two subsets of S. And over time, if you gave me every single subset of S prime, I could give you every single subset of S in this way.
Right, yeah.
Nothing would be missing. It'd be exactly the same. All right, so now that we have that, well, S prime, maybe I'll write this over here. Oops. What's the size of S prime? So not the power set, the set itself. Right, it's the size of S minus 1. We said up here that S is a set of size k plus 1. So that's k plus 1 minus 1, which is k. So the size of S prime is k. And our inductive hypothesis says that the size of the power set of a set of size k is 2 to the k. So therefore, the size of the power set of S prime is 2 to the k. That's the same thing. Well, the number of subsets of S is the number of subsets of S prime times 2. So let's write that again. The number of subsets of S is the number of subsets of S prime times 2. Well, the number of subsets of S, that's exactly the same as the size of the power set of S. Right? And the number of subsets of S prime, that's exactly the same as the size of the power set of S prime. And then we have this times 2 out here. So we know that the size of the power set of S prime is 2 to the k. And that's times 2. So that's 2 to the k plus 1. So this says that the size of the power set of S is 2 to the k plus 1. And if you look at what it is we were trying to show, it was exactly that. The size of the power set of a set of size k plus 1 is 2 to the k plus 1. And this intuitively makes sense, hopefully, because every time you add a new element to a set, well, if you look at the list of subsets, it's going to double it because you take every subset that was there before and either add it or don't. So those are the two possibilities. So that's why the size of the power set increases exponentially. Any questions about this one? So this is another kind of tricky one because you're not just, proving that some equality is true. You're exercising a little bit of logic and explaining what's going on in words. But that's okay. You should be able to do that. But you follow the same kind of steps. All right, so let's do another one. This is something, again, we've seen before, but we're ready to prove in a different way. So I'll prove that the sum from I equals 1 to n of I is n times n plus 1 over 2. Right, so this is the proof that the sum of the first n positive integers is n times n plus 1 over 2. All right, so we do the usual thing. We start with the basis step. And in the basis step, while the sum goes from I equals 1 to n, so the smallest that n could be is 1. So n equals 1. Okay? In fact, you could start this at 0 and everything would be fine. But the way it's written strongly implies that you should start at n equals 1. Again, doesn't really matter, and on a test or something I would tell you exactly where to start. All right, so when we have n equals 1, the left-hand side is the sum from I equals 1 to 1 of I, which is just 1. And the right-hand side is 1 times 1 plus 1 over 2, which is 1 times 2 over 2, which is 1. So we have left-hand side equals right-hand side, and we're happy. So that's the basis step. The next step is the inductive hypothesis. And here we want to assume that the sum from I equals 1 to k of I is equal to k times k plus 1 over 2. And this is for some arbitrary k. You might also see for some fixed k. That means the same thing. So you could just as easily write fixed here. All right. So now we do the inductive step. And you always start the inductive step with what it is you want to show. So I want to show that the sum from I equals 1 to k plus 1 of I is equal to what?
K plus 1 times K plus 2 over 2?
Yeah, k plus 1 times k plus 2 over 2. I go up to the statement and I sub in k plus 1 for n. So that's k plus 1 times k plus 1 plus 1. Just k plus 2 all over 2. All right, so we do the usual trick for working with the summation. We start on the left side, so I equals 1 to k plus 1 of I. And we split that up into the part we know about and the part we don't know about. I know something about the sum from I equals 1 to k. So that's the sum from I equals 1 to k of I. And after I make that, after I take all those terms, what's the very last one? Right, the very last one is k plus 1 that I didn't add. And notice this time there's only one term. And the reason there's only one term is because the upper limit of this sum is a linear function, if you like. Right? It's just k plus 1. So that splits up into k and then the last one. All right, so now that I have that, I can apply what I know. I know from my inductive hypothesis that this thing here is just k times k plus 1 over 2. And I have this other k plus 1 there. All right, so I want to add these things together. So I have a common denominator of 2. And watch your brackets here. So the 2 applies to both of those things. And now I do, a little bit of work. So I could expand this out, and that's probably the easiest way to see it. K squared plus k plus 2k plus 2. And this is all over 2. So this is k squared plus 3k plus 2 over 2. What's that the same as? Yeah, I mean, that's the hope, right? So if you don't remember how to factor, that's okay. We know that this is what we're going for, right? We know that that's what we want the answer to be. So just work backwards, right? K plus 1 times k plus 2 over 2. Well, that's k squared plus 2k plus k plus 2. And that's the same as k squared plus 3k plus 2. Right? So if you're not a factoring expert, don't worry. Just hope that it's the answer and work backwards. And if it isn't, then you've probably made a mistake somewhere. Okay? Does that make sense? All right, so we'll do another one, because the only way to get good at these is to see lots and lots of examples. This next one is going to be prove that 2 to the n is less than n factorial. And that is for all positive integers n greater than or equal to 4. So here's an example of one where we're proving it for something that's not 0 or 1. The basis step will be n equals 4. Why do we do that here? What happens if you subbed in n equals 3? So it's 2 to the 3? Yeah. 2 to the 3 is 8. 3 factorial is 6, so it says 8 is less than 6, which isn't true. So that's why it says n is at least 4. So in the basis step, we have n equals 4. And the left-hand side is 2 to the 4, which is 16. The right-hand side is 4 factorial, which is 4 times 3 times 2 times 1. So that's 12 times 2 is 24. And we have 16 is less than 24. So the left-hand side is less than the right-hand side, just like we wanted. All right, so now we do our inductive hypothesis. And that is assume that 2 to the k is less than k factorial for some arbitrary or fixed k. I usually say arbitrary, but people do say fixed, and I want you to be able to read that if you see it. All right, so what we have to do in our inductive step is we have to show that 2 to the k plus 1 is less than k plus 1 factorial. That's what we have to show. And this is an example where the fact that you're using an inequality is really important. Yeah?
You have to state your descriptions.
To be fully correct, yes, you probably should. Yeah, it's not a bad idea. All right, so we want to show this thing. This is an inequality, which means we start on one side and work our way to the other side. So we start with 2 to the k plus 1. Well, we know that's the same as 2 times 2 to the k. Right? And we know something about 2 to the k. We know that 2 to the k is less than k factorial. So 2 times k factorial. So 2 times 2 to the k is less than 2 times k factorial, and that's because of the inductive hypothesis. All right, so given that we know that, we need to do a little bit more work. So what's k plus 1 factorial the same as?
K factorial times k.
Not quite, k plus 1, yes. So we know that we want k plus 1 times k factorial. That's what we're shooting for. We have 2 times k factorial. Is that good or bad? It's good. It's really good. It means we have a lot of slack. But at the same time, that's what makes this kind of thing very difficult. Because for the most part, in my experience in this course, people have a lot of practice through elementary and high school working with equalities. But what you probably don't have as much practice in is working with inequalities. Because with inequalities, you can somehow be very imprecise, right? 1 is less than a billion, right? By a huge factor, but that's just as true as 1 is less than 2. So you're not being imprecise in the sense of true or false, you're sort of being loose in terms of how far off you are from the number. So this thing here is less than k plus 1 times k factorial. And the reason for that is that 2 is less than k plus 1. Because 2 is less than k plus 1 is exactly the same as what? Well, so if I have 2 is less than k plus 1, that's the same thing as 1 is less than k, which is the same thing as k is bigger than 1. But I already know that k is at least 4. So if k is at least 4, then it's certainly bigger than 1. So that's why this step is valid. It's very easy to find yourself in a situation where you wouldn't be able to apply this for whatever reason. You need to check to make sure that it's valid in terms of the statement. If the statement was about something for k being at least 0, then I wouldn't be able to do this, right? Because k has to be bigger than 1 for this step to hold. But I already know that it's at least 4. And at this point, I'm basically done because that's just k plus 1 factorial. So this proves that 2 to the k plus 1 is less than k plus 1 factorial. Does that make sense? So this is a tricky example because the proof, the statement is very true. It's true by a wide margin. And it seems like that should make it easy to prove, but a lot of people find that that makes it difficult to prove because you do need to be a little bit loose with your inequalities to make this work. All right. So I'd like to do 2 more examples. So here's one example. I'd like to prove an extension of De Morgan's law for sets. So I'd like to prove that if I take the intersection from j equals 1 to n of aj and take the complement of that. So I haven't used this notation before. This notation is to intersection as the sigma notation is to plus. So I'm going to, this is the same as a1 intersect a2, intersect a3, intersect a4, all the way up to an, and then take the complement of the whole thing. And the claim is that that is the same as the union from j equals 1 to n of the complement of aj. So when n equals 2, this is exactly De Morgan's law. I'm saying a similar thing works for any number of sets. So if you want to see an example, A union, A intersect B intersect C complement, this is saying it's the same as A complement union B complement union C complement. That's all that's saying, except it's not just true of 3 sets, it's true of any number of sets that you'd like. Is the claim clear? Yeah? Oh, yeah, so the complement there is in this question, not in the last question. All right, so let's do a proof of this. We start with a basis step. And the basis step, well, what's the smallest n can be? You could make a strong argument for both. If n was 1, then this would be the intersection of aj with nothing, so just aj, and that would be the complement of aj, and this thing over here would be the union of complement of aj with nothing, so just the complement of aj. So it is in fact true when n equals 1, but I'm going to show you for n equals 2. All right, so when n equals 2, the left-hand side is a1 intersect a2 complement. The right-hand side is a1 union a2, where both of them are complemented. And we know this is true because this is De Morgan's law. And if you still don't believe that that's true, then do a membership table, and you'll see that it is.
How are you supposed to prove it?
We don't have to prove that because I gave you De Morgan's law. I said you can take that to be true. If I hadn't done that, then you'd have to do a membership table, yes. All right. So next we have the inductive hypothesis. And for that we assume that the intersection from j equals 1 to k of aj, all complemented, is the union from j equals 1 to k of aj complement. That's our inductive hypothesis. And now we do our inductive step. For this, I want to show that the intersection from j equals 1 to k plus 1 of aj, all complemented, is equal to the union from j equals 1 to k plus 1. What's going on there? That's weird. J equals, no. aj complement. That's what I'd like to prove. So I'm proving something about an equality, so I should start on one side and work to the other. And I'm proving something that's kind of like a sum, so I'll split off the part I know something about. That's what we'll do. So I start on the left side. So the intersection from j equals 1 to k plus 1 of aj is what I'll start with. Well, this is exactly the same as ak plus 1 intersect the intersection of j equals 1 to k of aj with the complement over everything. Right? All I'm doing is I'm splitting apart that intersection in the exact same way that I would split up a summation. Does that make sense? All right, so now that I have that, I can work with this. I can do something. What is this thing right here? It's a set, right? That's not a trick question. So let me actually do that in a different color. This thing here is a set. And this thing over here, the result of taking a bunch of intersections, is another set. So that means I can use De Morgan's law. De Morgan's law works if you have two sets. So this thing here is exactly the same as ak plus 1 complement union the intersection from j equals 1 to k of aj complement. Does that make sense? I'm treating that big intersection as one single set, because when you intersect a bunch of sets, you get a set. Is that okay? All right, so now I know something about this set, and I know because of my inductive hypothesis. I know that this thing here, the intersection from j equals 1 to aj, all complemented, is equal to the union from j equals 1 to k of aj complement. So the union from j equals 1 to k of aj complement. So now I'm in pretty good shape because this is a union and these are all unions. So I can write this exactly the same as the union from j equals 1 to k plus 1. Right? Over here it's just to k, but I'm also going to union on this set right here. And that is of aj complement. Does everyone see how I did that? I'm just incorporating that last set into my big union. All right, so now that I've done that, I'm happy, because if I look back at what I was trying to prove, that's exactly what I was trying to prove. Any questions about that? Okay, so I'm not going to start the other example because I won't be able to finish it tonight. So we'll leave it here for tonight. Next time we'll see a few more examples of induction.